All right, I'm going to go ahead and get us started. Good day, everyone. My name is Amy Lambert. I'm EA's Director of Communications, and welcome to this webinar providing an update on chemicals and contaminants of emerging concern. Now, I'd like to introduce today's speaker. Paul Caprio is Vice President and Director of Chemicals and Contaminants of Emerging Concern at EA. He has more than 43 years of experience and serves as our subject matter expert for more than $170 million in PFAS work. Welcome, Paul. I'm going to turn it over to you.
Okay, thanks, Amy. Wow, that photo is slimming. I wish I was that slim. Well, good afternoon, everyone. Here at EA for the last 4 years or so, we've established a service area that we call Chemicals and Contaminants of Emerging Concern, or CCEC. It brings together subject matter experts in the fields of risk assessment, contaminant fate and transport, chemistry, and other scientific and technical fields who are supported by our in-house treatability and ecotoxicological testing laboratories. The purpose of this group is to contribute to the advancement of science through research and execution of projects related specifically to contaminants of emerging concern. Everything from innovative site innovation techniques, environmental forensics, modeling, to technology development is part of this program. It has been dominated by per and polyfluoroalkyl substances, or PFAS, but we've also been keeping an eye on other contaminants of emerging concern. As a director of this program, I've devoted most of my time to PFAS. So full disclaimer, I'm not a subject matter expert in every other COC. I'm still learning too, but we have other folks on staff that are. So I'm a big believer in keeping things very simple. So let's look at some of the basics on what we really need to know about contaminants of emerging concern, or CEC. There's some basic questions that we have to answer regardless of the chemical compound. Is a chemical substance potentially harmful? Sometimes we have the data to back up our assessments. Other times we may not, or at least it may not be readily available. Is there a likelihood that there could be unintended exposure to potentially hazardous levels? It could be through occupational exposure, for example, firefighters' exposure to aqueous film-forming foam, or AFFF, or incidental exposure to contaminated drinking water. It may not always be such a human health hazard, but can it harm ecosystems? Say, for example, resulting in high mortality of certain aquatic species that are relied upon for commercial fishing. So in this case, it would be also an economic impact as well. Is it a regional, national, or even a worldwide phenomena where large populations are at risk? And is the science reliable? Is there general agreement on the toxicity, fate, and transport? This is typically where we find ourselves at loggerheads within the scientific community, and is also frequently a catalyst of much debate and even litigation. And finally, is it or will it be regulated? And is there general agreement on how this regulations will be applied? Again, we find that reliability of science will again enter into the conversation and call it into question. Next slide, Amy, if you would, please. So our presentation today summarizes how certain chemicals are classified as CEC. It takes a quick look at the recent EPA federal MCL rule for 6 PFAS and some of its implications on our nation's public drinking water systems. Then we'll take a look at some of the current front runners on the CEC landscape beyond PFAS. But let's also be mindful that we certainly haven't seen the last of regulations geared towards PFAS, which in my opinion may overshadow other CEC for the foreseeable future. The other thing I would like to note is, as we have seen with PFAS, is that the scientific and regulatory landscapes for some of these COCs are very fast-paced and evolve rapidly. And there are also many other CECs not listed on this slide. Next slide. We also use the term emerging contaminants sometimes, or EC. However, the EPA's Office of Water has moved away from this term towards contaminants of emerging concern. The distinction is that it's not the contaminant that's emerging, it's the concern that's emerging. This term equally applies to newly discovered contaminants or chemicals, or contaminants or chemicals that have been around for a while and now we're just realizing that they may be more toxic than we originally thought. A newly discovered source, or an exposure pathway, lack of or updated toxicity data, high occurrence in drinking water sources or in surface water, or even the perceived threat to humans or the environment, are all potential springboards leading to an interest as a CEC. Next slide. As I previously mentioned, there are a few ways that CECs become of interest. The Unregulated Contaminant Monitoring Rule, or UCMR, is a process where EPA looks at a potential list of contaminants of concern under the Safe Drinking Water Act. This act requires that EPA monitors for priority unregulated contaminants every 5 years by first narrowing down a larger contaminant candidate list, or CCL, to a list of 30 or so chemical or biological contaminants to monitor for in all public drinking water systems that service more than 10,000 people and a subset of smaller systems. The agency will then evaluate whether or not the contaminants warrant further investigation or potential future non-binding health advisories or potential future maximum contaminant levels. This is referred to as a regulatory determination. As we have seen, we now have MCLs for 6 PFAS that have gone through the third iteration of this process, referred to as UCMR3, that occurred between 2012 and 2016. UCMR4, which was conducted between 2017 and 2021, did not include any PFAS, but did focus on 10 cyanotoxins, which we're going to talk about today. And the UCMR5, which is occurring now, is revisiting a larger list of 29 PFAS using lower analytical detection limit capabilities than were previously available during the UCMR3. And EPA has published the results of 3 or 4 rounds of the latest round of public water sampling, which have shown that approximately 10% of the facilities sampled have one or more PFAS above the current MCLs. However, CEC can be identified in other ways. For example, state-led programs. Some states actually move faster than the federal government in passing regulations. Michigan, for example, has approximately 270 known PFAS sites that are undergoing investigation process now under their state program. International programs. Australia, the EU, and Canada often act before US, as was the case with PFAS. Scientific studies frequently inform us on occurrence, fate, and transport or risk of CEC, and sometimes even public awareness of potential risk can be a big driver of action, to the point where the Interstate Technology Regulatory Council, or ITRC, its current CEC guidance documents under development include a section on outrage management. Next slide, Amy. Another way to regulate these compounds is through the Toxic Substance Control Act, or TSCA. In this manner, chemicals of interest are addressed by a 3-phase process. First uses criteria such as hazard, exposure, persistence, bioaccumulation, or other discretionary criteria to designate a chemical either as a high priority or low priority substance. If EPA designates a chemical as a high priority substance, the chemical moves to the risk evaluation phase to determine whether or not the chemical presents an unreasonable risk to health or the environment, and finally, to a risk management response phase via some sort of regulatory action on the manufacture, processing, distribution, use, or disposal of a chemical to eliminate the unreasonable risk. The significant new use rule, commonly referred to as SNUR, is an example of how certain PFAS, for example, PFAS, was regulated out of use in many projects in the early 2000s. The next slide. While regulatory agencies are working their way through the PFAS issue, they're also looking towards what is the next big thing. The federal government's approach is to establish a joint committee consisting of 17 federal agencies, whose goal is to come up with a framework to identify and respond to the next group of CECs. It's interesting to note, though, that the framework is explicitly set up for CECs in drinking water, so that things like 6-PPD quinone that primarily affect fish won't be addressed by this framework. On the state and local level, as I mentioned earlier, some states spearheaded the 2023 ITRC working group, whose goal was to develop a separate framework for them used to identify and react to new CECs. This group is planning to publish their guidance document sometime this year. Meanwhile, some states also choose to push forward with research, investigations, and solutions on new CECs themselves. Much of this legislation and funding associated with these non-PFAS CECs has to do with preventing future releases rather than cleanup of existing contamination. So this includes things like plastic bag bans, extended producer responsibility laws, which require plastic manufacturers to be stewards of the product through their life cycle by contributing to recycling programs. Next slide. So let's take a look at the recent PFAS MCLs and some potential implications. EPA's primary message about this rule is that PFAS do cause adverse health effects to humans from exposure to drinking water across all regions of the U.S., with a disproportionate impact on small and disadvantaged communities. EPA has estimated the cost of public utilities to comply with this rule to be about $1.5 billion annually, which by most other accounts is considerably low. Next slide. So EPA has set a maximum contaminant level, or MCLs, for 5 PFAS and added a 6 PFBS for use in calculating the hazard index, or HI, when there's a mixture of more than 1 PFAS as shown on this table. These values are very low. They're in the parts per trillion range. And in situations where PFAS or PFBS is part of the HI calculation, a value of 2,000 parts per trillion is used. So you may ask, why are these maximum contaminant level goals, the MCLGs, which are also listed on this table for PFOA and PFOS, set at 0? Next slide. Well, for PFOA and PFOS, EPA's default position when setting protective exposure levels for carcinogens is that no amount of exposure is safe. This is known as the nonlinear threshold dose response model. So they set an unenforceable MCLG at 0. However, you can't regulate to 0. So EPA sets enforceable limits that can be reliably detected or treated with best available technologies. It is noteworthy that these U.S. standards are lower than our European or Canadian counterparts that are generally have levels in the hundreds of parts per trillion range. There is and will be much debate and for certain future litigation concerning these low MCLs and the wide discrepancy of numerical standards when only about 20% of the PFAS intake is directly from drinking water consumption. Next slide. So what are some of the rule requirements? Well, the basic rule requirements are that public water systems, drinking water systems, will have to complete their monitoring protocols within 3 years, by 2027. And if they have exceedances of 1 or more of the MCLs, they'll have to comply with the numerical standards by 2029. That gives them about 5 years to react to this rule. So this could involve anything from putting a new treatment system on an existing drinking water facility, retrofitting, or alternatively shutting down contaminated wells or finding new sources of clean drinking water. Next slide. I'll zip here. This is a monitoring decision flow chart that EPA put out that defines the frequency of monitoring based primarily on the size of the facility and how it can be adjusted for sampling either up or down in terms of frequency if they approach actionable levels, which are referred to as trigger levels in this case. In this case, if MCLs are exceeded, actions would be required, such as treatment or, as I said earlier, alternative sources of water be developed. Next slide. So who's affected by this rule? Based on the recent UCMR5 sampling results and prior estimates by EPA, approximately 10% of the public drinking water systems will likely have to take some kind of action to reduce PFAS levels. Something on the order of more than 6,000 systems across the U.S. of varying sizes That translates to upwards of 100 million people that could be affected. This will definitely put a strain on the supply of treatment media that are commonly used for drinking water treatment, as well as qualified vendors and contractors to do the work. The next slide illustrates how these numbers were derived. I've rounded off the numbers on this slide to make it a little easier, but it illustrates that there are approximately 150,000 public water systems nationwide. That includes both surface water and groundwater. Public water systems are further characterized by community or non-community systems. Community water systems, as shown on the right, are then further subdivided by the number of customers they service as small, medium, or large. All community water systems are subject to the MCL rule. That represents approximately 50,000 community water services or systems that serve more than 300 million people across the U.S. On the other side of the chart, we have non-community systems that are further subdivided into transient and non-transient systems. Transient systems, say for example, a campground, are not regulated under this rule. Next slide. I had mentioned earlier that EPA's estimate for cost to comply was about $1.5 billion annually. Other estimates from the American Water Works Association are much higher at about $3.2 billion. And of course, neither have taken in consideration state and municipality regulatory agencies and the cost they'll incur by both oversight and enforcement actions. Rate hike estimates vary over a wide range as shown here, with the smaller systems getting hit disproportionately higher with higher per customer rate hikes, as they will have less customers to pass the capital and O&M cost on to. Next slide. There really is only a few proven PFAS treatment technologies that can be economically scaled up for public drinking water systems at this time. As shown on this table, granulated activated carbon and ion exchange resins are the two most common methods used, with reverse osmosis being another. All these technologies remove PFAS to a varying degree and are pretty effective, but there's still residual waste that must be dealt with either through disposal in a landfill, incineration, or thermal or chemical reactivation. This will ultimately also place a high demand on GAC and ion resins in the marketplace, and I think provide additional incentives for commercialization of other alternative treatment technologies. Next slide. So who pays? The MCL rule is not set up to hold polluters accountable directly. While there is some relief to water utilities in terms of forgivable loans and grants through the bipartisan infrastructure law, these funds will eventually be exhausted and underfunding mechanisms will be needed. The most likely way of passing cost on to customers is to pass cost on to customers. Litigation is another option being pursued in multi-district class action suits against DOD and major manufacturers, but I personally don't think this is going to be sustainable funding mechanism over the long term. Next slide. So I said we'd touch on a few other CECs, particularly those that are, in my opinion, of a potential concern nationally, with the exception of 6 PBDEs, which seems right now to be more of a West Coast issue. I want to point out that none of these listed have begun to approach the attention that PFAS has received either publicly or from the scientific community. Although a couple listed here are intimately woven throughout the fabric of our society, even more so than PFAS, such as pharmaceuticals and microplastics, which are such a big part of our everyday lives. Next slide. So, okay, the first one I'm going to touch on is microplastics and nanoplastics. Next slide. So worldwide, 460 million tons of plastic are produced per year. Most does not get recycled and ends up in a landfill or released in oceans or freshwater systems. And by and large, MP are not biodegradable. In oceans alone, plastic pollution estimates are between 4 and 14 million tons per year. By some estimates, microplastic contamination may reach 12 billion tons in our oceans by 2050, and by some counts, outnumber the volume of the volume of fish that's currently in the oceans of the world. Microplastics are small debris less than 5 millimeter long. This can include weathering, for example, abrasion or subjection to UV radiation of larger plastic items such as bags, plastic bottles, or tire wear particles. Microplastics are present in everyday products such as clothing, the nylon fibers, cosmetics, and they contain potentially harmful chemicals such as phthalates, polybrominated diphenyl ethers, and other additives that can leach out into the environment. Equally concerning is that microplastics can absorb and transport other contaminants, such as heavy metals, organic pollutants, such as 6-PBDEs from tire wear, and even PFAS. A subgroup of microplastic is referred to as nanoplastics. Nano refers to a billionth of a meter, and nanoparticles are generally in a range of 1 to 100 nanometers. To put this into perspective, the average human hair is about 25,000 nanometers wide, and the head of a pin is 20 million nanometers wide. So we're talking about some pretty small particles here. Next slide. Common sources of microplastics that are released into the environment are sewage treatment plants, cosmetic and clothing industry, manufacturing, packaging, and shipping. Human exposure to microplastics is through primarily ingestion through drinking water or inhalation. In addition to recycling or alternate materials used for packaging to mitigate microplastics, some of these plastics are being used as additives in building materials such as concrete and asphalt. They're used as incineration for energy, and there's ongoing research into a number of bacteriological and fungal species that possess the capabilities to biodegrade some of these plastics like polystyrene, polyester, and polyethylene that could be introduced into treatment plants. Next slide. Human exposure to microplastics is through ingestion or inhalation. Some environmental scientists suggest that the average person may be ingesting or inhaling the plastic mass of a credit card every week. Although most of these particles are likely filtered out of the body's waste systems, microplastics pose a risk to humans physically, chemically, and are a host of other microorganisms to gather and breed. There are several ways that we can look at microplastics in the environment. Visual observation with the naked eye or through magnification to identify particle size and shape. We can quantify the amount of particles, particle count or mass of microplastics per unit volume. And of course, we can look at the chemical makeup through laboratory analysis such as gas chromatograph mass spectrometry. Next slide. So federal regulations addressing microplastics include the Microbead-Free Waters Act of 2015. This law prohibits the manufacturing, packaging, and distribution of rinse-off cosmetics containing plastic microbeads and defines microbeads as 5 millimeters or less in size. In 2020, the Save Our Seas Act 2.0 was signed into law. Although not directly pertaining to microplastics, it provides grant funding for new research and development of microfiber pollution prevention strategies. In March 2022, Congress passed the Bipartisan Infrastructure Law and Jobs Act. This law gave U.S. Environmental Protection Agency $50 billion to invest in the nation's drinking water. The EPA issued a memorandum that reaffirmed that the state revolving fund provisions of the bill include microplastics, including from tire wear. As far as the states' regulations, 16 states in the U.S. and all U.S. territories have enacted some type of ban on plastic bags, straws, styrofoams, etc. 6 states have enacted primary microplastic regulations aimed at phasing out microbeads. California is the only state at this time to have microplastic regulations focused on reducing oceanic pollutions, although Florida is now attempting to address microplastic cleanup in aquatic and terrestrial environments as well. Next slide. So our next one up is 6-PPD quinone. Next slide, Amy. So 6-PPD and 6-PPD quinone are another set of CECs that are getting attention and are also linked to microplastics in the tire wear, which is a form of microplastic, is a major contributor to 6-PPD release in the environment. 6-PPD is used as an anti-degradant in tires. As tires degrade, they shed microplastics, and 6-PPD on those particles reacts with ozone in the environment and transforms into a more stable and persistent 6-PPD quinone. These particles are then transported from roadways via runoff into surface water where they can threaten aquatic life. 6-PPD quinone gained notoriety a few years ago when it was implicated as one of the primary causes of coho salmon in the streams near urban areas of the Pacific Northwest. In 2020, researchers identified 6-PPD quinone as one of the most toxic chemicals to certain aquatic species. This was based on a study that exposed 135 juvenile coho salmon to 6-PPDQ, resulting in a 98.5 mortality. When the same study was repeated with other tire chemicals, none of the fish died. For the most part, although 6-PPDQ has been a West Coast or Northwest Pacific issue, it has also been linked to toxicity of other fish species, such as rainbow trout, which make it more of just a West Coast issue. Other states, such for example, Minnesota and Maine, have included 6-PPDQ as a chemical of concern. Interestingly enough, recycling of old tires to be ground up into rubber crumb, used to create synthetic turf or playground floors or road banks, is, while being considered a beneficial reuse, in light of its relationship with 6-PPDQ, the reuse of tires in this way may also be a bigger environmental issue that we have to look at that is more widespread across the U.S. We can look for 6-PPDQ in the environment by analytical methods. EPA recently published a draft method 1634, which is a solid phase extraction liquid chromatography tandem mass spectrometry method. Research is still ongoing on whether or not 6-PPDQ is toxic to humans or other land animals. There are some indications of possible liver and kidney effects in humans. There are not many regulations in effect under consideration at this time for 6-PPDQ. California has adopted a rule that will require tire makers to find new alternatives to chemical 6-PPDQ that is currently in use. EPA has also indicated back last November that they would publish sometime in late 2024 an advance notice of proposed rulemaking under the Toxic Substance Control Act to ban 6-PPD in tires. Next slide. So let's talk a little bit about cyanotoxins. Next slide, Amy. Cyanobacteria are microscopic bacteria that live in all types of water bodies and can grow into blue-green algal blooms that can pollute water. Some cyanobacteria have the ability to produce toxins called cyanotoxins, which may be toxic to animals and people. Ingestion of these cyanotoxins in small amounts can cause gastrointestinal symptoms, while larger amounts may cause liver or neurological damage. Cyano harmful algal blooms can cause dissolved oxygen swings that may result in plant and animal die-off. Next slide. Different cyanotoxins have different effects. Acute complications include digestive problems. Longer-term exposure could include impacts on the liver, kidney, skin, or nervous system. Effects on cyanotoxins in fish include endocrine disruption and mass fish kills. Effects on bird include neurological complications. Dogs that may lick or drink water that are contaminated with cyanotoxins can be also at risk, including death. And of course, there are also a number of other economic effects through loss of fishing or agricultural resources of these harmful algal blooms. Next slide. Cyanotoxin or cyanobacteria are currently not regulated by the federal government. However, in June of 2015, EPA released 10-day drinking water health advisory levels for 2 cyanotoxins for children younger than 6 and for children older than 6 and adults. There are both field methods called enzyme-linked immunosorbent assay, or ELISA, and lab methods that can detect cyanotoxins, the most robust being liquid chromatography tandem mass spectrometry. EPA has published their final recommended recreational ambient water quality criteria or swimming advisories for 2 cyanotoxins under the Clean Water Act. To date, 5 states have proactively issued guidance or regulations for cyanotoxins in drinking water. Other states, I believe, including Maryland, also intend to take action when sample results indicate levels are above the health advisory. At least 30 states publish either an advisory for public beaches or a map where harmful algal blooms are present. Most of the remaining states list basic information about harmful algal blooms with no links to advisories or information about monitoring or sampling efforts. Next slide. One of the issues with cyanotoxins is the treatment cost. It's difficult to remove these contaminants from drinking water or wastewater. It requires a lot of additional disinfectant byproducts. For example, several municipalities in Ohio, in Oregon, and Texas each have spent more than $50 million to upgrade their systems for advanced oxidation with ozone and other treatment technologies. Next slide. So pharmaceuticals is another CEC. You could add personal care products to this category as well. And I believe that pharmaceuticals are kind of a tough group to get a handle on, frankly speaking, because we all benefit from their use in terms of improved quality of life. But hormones and pharmaceuticals are widely used for treatment of humans, domestic animals, livestock, and they have a potential to enter the environment. A little less than half of all medications prescribed over the counter or prescribed end up getting discarded. Even when consumed, some of these pharmaceuticals can end up in our wastewater streams after naturally passing through a person's body. Discharges from wastewater treatment plants, septic systems are all potential sources of hormones and pharmaceuticals because they're not substantially set up to remove these with their typical treatment processes. Next slide. One of the potential concerns is that unintentional exposure to some of these bioactive compounds in drinking water could result in adverse health effects to humans at low doses, including endocrine disruption and antibiotic resistance. There's also a potential for ecological impact. Next slide. For the most part, hormones and pharmaceutical compounds are not regulated in drinking water in the U.S. But back in 2017, 9 hormones were included in the 4th contaminant candidate list, which was then further narrowed down for the UCMR4. However, none of those hormones were retained for monitoring in our nation's drinking water systems. To treat some of these pharmaceuticals, we would have to be looking at, again, at some type of advanced treatments such as ozone or other absorptive media that you commonly don't find in most wastewater treatment plants. Next slide. So the last one I'm going to talk about is polybrominated diphenyl ethers, or PBDEs. Next slide. So PBDEs are a class of halogenated flame retardants that are commonly used in a wide array of consumer goods. Examples include furniture, foam padding, wire installations, rugs, draperies, upholstery, plastic cabinets, personal computers, televisions, and small appliances. Because PBDEs are not chemically, because they don't chemically bind to polymers or textiles or plastics, they can leach out when washed down a sink or shower drains, or become part of household or office dust, where they can be present at high concentrations. Also, they can be introduced into water and air by manufacturing or disposal of household appliances. They are bioaccumulative, build up in the environment over time. They're lipophilic, which means they're stored in fat. In animal studies, these chemicals have shown some effects on the thyroid and liver, as well as brain development. However, more research is needed to assess the health impacts to humans. However, in some respects, our preliminary outlook on PBDEs sounds really familiar to what and how we looked at PFAS less than 10 years ago. We can quantify these compounds in the 8 conjugates of interest by high-resolution gas chromatography and high-resolution mass spectrometry. There is an EPA method 1614, with capabilities to detect these compounds down to the parts per quadrillion range in aqueous samples. There have been some significant new use rules, or SNURs, under TSCA, requiring notice to the EPA prior to manufacture or import of articles which contain certain PBDE conjugates, and there was a voluntary phase out of some of these conjugates back in 2004. Approximately 10 states have banned 2 PBDE conjugates, and states such as Washington, Maine, Maryland, and Oregon have also introduced legislation that bans the sale of certain products that contain these chemical compounds. Next slide. But let's not forget PFAS. Although it will be interesting to see how all this plays out over the next 5 years, if any of the CECs we discuss rise above others in terms of interest, or if there's something else that we haven't covered that may be of more interest, PFAS will continue to dominate the landscape and will probably never fully evolve out of the place as its place in the CEC domain anytime soon. The UCMR 5 is underway with testing of 29 PFAS, and recently 2 PFAS, PFOA and PFOS, were designated hazardous substance under CERCLA, which will empower EPA and states to hold polluters liable. We can expect EPA to set categorical effluent limitation guidelines over the next few years for a couple industrial categories, as well as possible air emission standards. But for all of those of us who've been in the environmental business for a while, we all know that there are certainly others out there on the horizon waiting to be part of the conversation. So this concludes my presentation. And again, I'd like to thank you for attending.
Now I'm happy to open us up to questions. Feel free to use the chat to type in a question and I can read it off to Paul. In the meantime, I'm going to switch over to our final slide, which will provide you with Paul's contact information, his email address, as well as a QR code link to information about EA's experience and expertise working on PFAS and other chemicals and contaminants of emerging concern. There is a question, Paul. Could you speak more to the funding of smaller drinking water systems?
Well, if you're talking about the Infrastructure Act, there's grant money, there's state revolving loans, forgivable loans, basically free money, I guess. And we've, where you can apply if you have, impacts on your drinking water system. It can also include pilot studies, some level of research, and man, we've seen a lot of state opportunities out there. Just the ones that we know of, 40 I've seen in the last several months. A lot of them have to do with, retrofitting their treatment systems. They have a known PFAS problem, and they need money to support either the engineering side or some of the science side. And it can I've seen grants in the millions of dollars. A lot of states have already applied for it. I think there's a list somewhere you can go to who's got what. And like as I said, I mean, it doesn't go on forever. There's a 5-year window, and there could always be more money set aside. But going back to the cost of the 1.5 to 3.2 billion dollars a year, which is probably an underestimate. Where's that money going to come from? And one of the slides, $3,000 rate hike. If you have a small system servicing a couple hundred people and you got to put in $1 million treatment system, well, that money is going to be spread out over a smaller population, and that's just not sustainable.
Great question. Thank you, Paul. Any other questions? All righty. Well, this will conclude our webinar for today. Again, oh, wait, one more just came in. How many projects does EA currently have that are investigating remediating PFAS contaminants, and what is the total dollar value of those projects?
Oh, well, I happen to know that one. We have, if you want the details, we're doing 33 remedial investigations for Department of Defense, some for EPA. We're doing what's called either preliminary assessment or due diligence at over 184 sites. Most of those are DOD. We have quite a bit of R&D work. I guess one of our specialties is thermal remediation. We've done a lot of work both under CERTIP and with private industry. We do a lot of work within our laboratory. So all told, we've got, I'd say well into the hundreds of projects and $180 million in the last 5 years.
Excellent. What do you think our current market share is in the emerging market?
What
or how big is the market, I would say?
Well, by some estimates, if you look at the Environmental Business Journal, and the way they do that is they canvass industry participants like EA and other companies that do it. Of course, there's a little bias there, but their numbers in the 200 billion range.
Wow.
I think other estimates looking at some of the out there are clearly in the 7 to 100 billion dollar range. And if you look at just the water, really where the biggest issue is going to be is wastewater treatment plants. I mean, not they didn't cause the problem. They're kind of third party innocent bystanders, but all the waste ends up there. So it's the drinking water, it's the wastewater, it's landfill leachates, it's the legacy contamination, both DOD and non-DOD. So when you add all that up, and the fact that every day there's a new regulation for PFAS, I think that snowball's getting bigger as it rolls downhill.
All right, well, this time I'm going to wrap up this webinar. Thank you all for joining us. And if you have more information, feel free to reach out to Paul via his email, pcaprio@eaest.com. Thank you, everyone. Have a great day.
Thanks a lot.